Hello there. So this question C, in the way they are, you have 0, 0, negative, negative 1. So this is what we have, and then it says equals 0. So equals 0. And by the time we find the determinant of this 3 square matrix, what we obtain is lambda cubed minus 5 lambda squared plus 8 lambda minus 4 equals 0. And this is exactly what we obtain. And then by the time we solve this cubic equation, what we obtain is lambda 1 equals 1, and then lambda 2 and 3 equals 2. That is, this one has a multiplicity of 2. So I'm going to go ahead to find the eigenvector that corresponds to this distinct eigenvalue here first, since that one is quite easy to get. So I want to find the eigenvector that corresponds to lambda equals 1. So finding the eigenvector is the same as solving a minus lambda I times x equals 0. So where x here is the eigenvector that corresponds to lambda. So since we are considering lambda equals, and it's for lambda equals 1, then we have a minus lambda I times x to be, so for lambda equals 1 now, so 1 minus 1 is 0, 3 negative 1 is 2, 1 negative 1 is 0. So that's going to give us 0, 0, 0, 0, 2, 1, and then 0, negative 1, 0. And then our x here is x, y, z equals 0, 0. That's the 0 that we have here. So the 0 here is the vector, so we have here. So what we want to do is to solve the system here, to solve this linear system here. So we want to row reduce this. So when we row reduce that, what we would obtain is we have 0, 1, 0, you have 0, 0, 1, then you have 0, 0, 0. Then we have our x, y, z equals 0, 0, 0. So this is exactly what we obtain. And then when we write this now in equation format, so we have 1 times y, that's y equals 0, 1 times z, that is z equals 0. And then we do not have x, so x is appearing nowhere, so that implies our free variable here. So our free variable is x. So since our free variable is x, we're going to set, you can set, like I told you, like I've said in the previous videos, you could set the free variable to be anything. That's why it's called free. You could give it any number, and then it still stays valid. So but let's set our x to be 1. So if we set our x to be 1, so the eigenvector that corresponds to lambda equals 1 is going to be k1 equals, so x, which is 1, y, which is 0, and z, which is also 0. So that's exactly what we obtain for the eigenvalue that corresponds to, the eigenvector that corresponds to lambda equals 1. So let's go ahead to find the eigenvector that corresponds to lambda equals 2. So we say for lambda equals 2, to find the eigenvector, so we solve a minus lambda I, the same equation, equals 0. So now for lambda equals 2, a minus lambda I times x equals, so we have negative 1, so we're replacing lambda with 2 in the coefficient matrix there, negative 1, 0, 0, 0, 1, 1, and then 0, negative 1, negative 1. And then our x is x, y, z equals 0, 0, 0. So this is exactly what we obtain. So the next thing we want to do is we want to write this, we want to row reduce this matrix here. Now on row reducing this matrix, what we would obtain is 1, 0, 0, 0, 1, 1, 0, 0, 0. Then we have our x, y, z equals 0, 0, 0. So this is exactly what we have. And then when we write this in equation format, So what we have is 1 times x, which is x, and that equals 0. 1 times y plus 1 times z, that's y plus z equals 0. And then the free variable here, is also, that's the free variable is z. So since the free variable is z, we're going to set z to be 1. So when z is 1, when it comes here, so we have y to be equal to -1, and our x is already 0. So our x is already 0. Then having gotten that, then we have the eigenvector that corresponds to the first eigenvector here is k2 equals 0, -1, and 1. And that's the eigenvector that corresponds to lambda equals 2. But then you observe, we are solving a 3 linear system. That's what we're solving here. So we are solving this 3 linear system here. And then the solution we expect should be x equals c1x1 plus c2x2 plus c3x3, where x1, x2, and x3 are 3 linearly independent solutions of the homogeneous system. But then we have 1, and then we have 2. So we need a third one. So since we do not have the third one, now to find the third one, now you recall that k2, that is the k2 I obtained here, was gotten from this equation here. And that is going to help us in finding the last one, as k3. So that is a minus lambda I times k2 equals 0. That is, k2 is the eigenvector that corresponds to this lambda. Now to find k3 must satisfy, that is the third eigenvector, a minus lambda I times k3. Now instead of 0, we're going to write the last eigenvector we got before, that is k2. So that's what we're going to use to find the next one. So let's go ahead now for lambda equals, for the same lambda equals to a minus lambda I times k3. So since we do not know k3, I'm going to assume my k3 is, say, x, y, z. So let's continue. A minus lambda I k3. So we're replacing a minus lambda I now. So a minus lambda I is the same matrix we obtained initially. That's the same thing we have here. So that's going to be -1, 0, 0, 0, 1, 1, 0, -1, -1. So this is what we have. We have x, y, z. Now equals 0, -1, 1. And this is exactly what we obtain. Now to solve this linear system here, we need to row reduce this matrix here. So you observe, when you're row reducing this matrix, you need to row reduce the augmented matrix, that is the coefficient matrix, and then the constant matrix here, the right hand side. So when we row reduce that, what we obtain is we obtain 1, 0, 0. We have 0, 1, 1, and 0, 0, 0 times our x, y, z equals, we have 0, -1, -1, 0. This is what we obtain now. Then when we write this now in equation format, we have 1 times x, that is x, equals 0. Then 1 times y plus 1 times z, as y plus z equals -1, and then that's all. And then when you look at these two equations here, you'd observe that our free variable, so the free variable we have here is z. So since the free variable is z, so we're going to set z. We'll set z to be 1. So, and again, I'm going to say it again, that you do not really have to set your z to 1. Your z could be anything. So all I need is just, I want to form the basis for the solution space of this linear system here. So z equals 1. So if z is 1, then my y is going to be, when we bring z to the other side, so my y is going to be 0 there, then my x is 0. So from there, I've been able to find k3. K3 is x, 0, y, 0, and my z is 1. So that's that for that. And then we said for this case the general solution, so the general solution is x equals c1x1 plus c2x2 plus c3x3. So where x1 is the one we obtained before, our x1 is just simply k1 a to the power lambda 1t. Our x2 is the one, this is the solution that corresponds to lambda 1 equals 8. Then x2 and x3, they are the solution that corresponds to the repeated eigenvalue. So their form is a little different. So for x2, the solution that corresponds to that is going to be k2 e to the power lambda 2t, while x3 is still k2t e to the power lambda 2t plus k3 e to the power lambda 2t. So we observe that here we have 1, but here we have 1 and t. So this is the one that corresponds to the repeated eigenvalue. That's why they look different. And then, so using the values we've gotten above, so we have that our x1, that's from above, we have from above that our x1, this is our x1 here. Our x1 is where do we have that? Yeah, here is it. So this is k1. So our x1 is going to be, we said it's k1 e to the power lambda 1t. So that's going to be 1, 0, 0 e to the power lambda 1. Our lambda 1 is 1, so e to the power t. So this is our x1. So let's go ahead and find x2. So our x2 is k2 e to the power lambda 2t. And our k2 is 0, negative 1, 1 e to the power, now our lambda 2t, our lambda 2, this is the second eigenvalue, which is 2. So that's e to the power 2t. And then to find k3, we said k3 is, so this is k3 here. I mean, so what are we using? So I meant x2, yes, this is x2. So to find x3, so this should be x3. So to find x3 is this formula here, which is k2t e to the power lambda 2t. So I'm just writing this whole thing back again just to register this thing into your memory. So what we have for k2 above was, so our k2 is 0, negative 1, 1. So that is 0, negative 1, 1 times t e to the power lambda 2t. So the lambda 2 itself, I do not really have to write that. So we have t e to the power, so since it corresponds to 2t plus k3, this is our k3 here, which is 0, 0, 1 e to the power 2t. So now we have our x1, x2, x3. So I did not need to write this. So we have the general solution. I'm going to write this whole thing back. So the general solution is x equals c1 times our x1 that we have just shown above. That is 1, 0, 0 e to the power t plus c2 times x2, the x2 that I just shown you above here, which is this. That is 0, negative 1, 1 e to the power 2t, and then plus c3, which is all that we have, c3 times x3. So this is our x3 here, so which is 0, negative 1, 1 e to the power 2t, this t e to the power 2t plus 0, 0, 1 e to the power 2t. Now this that we have here is the general solution. Is the general solution of the linear homogeneous system.